All right, just checking. Can everybody see this?
Yes.
Perfect. So good morning, everyone. And today I'm going to talk about C++. And the focus is a bit different than the earlier talks that we gave this week, where we showed some code on the computer screen. And those talks were designed more to discuss JEDI applications and some generalities about what's called object-oriented programming, whereas this talk is going to focus more on the essential features of C++ itself, and also focus on some of the libraries and the best practices. So there are two parts to this talk. It's split across today and tomorrow, and the two parts will try and answer two separate questions, basically why and how. Why is C++ the way that it is, and how can you effectively use it? And hopefully by the end of this one, you'll be ready for this morning's practical exercise. So let's start with the first of these why questions. Why do we care about C++? And the answer really is simple. We want a programming language that can produce very fast code that also has support for the expressive patterns that we're using inside of OOPS and inside of UFO. We want to have compile time produced interfaces instead of runtime produced interfaces between the core of JEDI and our models. And really, programming languages are not at all equal. They have their own different benefits and drawbacks. And in practice, OOPS was barely even possible with Fortran. And moreover, Fortran doesn't really have much new development these days. There are not many libraries or tools that we could easily build on, and we did not want to have to do a lot of the development for these in-house. Now, Python could have provided some of these benefits, but it also wasn't likely that we could have extracted enough performance out of it. So again, we want very fast code that we can implement operationally. And we have done surveys of Academy participants in the past, and attendees of the last Academy back in February indicated that they were mostly unfamiliar with C++, and only really about 60% of the audience had any familiarity with object-oriented programming. So if you are one of the people who does know C++ and is familiar, just please bear with me. But otherwise, this talk is going to be geared more towards the introductory or explanatory side, where I'll explain the concepts of C++ and give a couple of examples. So I want to just give you a broad overview and make sure that you're comfortable with at least reading the structure of the language. And then when you want to actually write any of it, then I'll give you some of those examples tomorrow. Now, that being said, there really is no substitute for practice, and I have some links peppered throughout this presentation, so if you've downloaded it, you can just click on those once again. And for those in need of a good tutorial, I'm going to recommend cplus.com. And if that one doesn't work for you, or if it's too technical, then there are a couple of tutorials provided by geeksforgeeks.org. Google is also going to be your friend here very much. It's also important to mention in C++ that there has been a very long development history, almost as long as Fortran. And before you get into bad habits, but after you get a little bit more familiar, I recommend reading perhaps the C++ core guidelines. And they were written by the creator of the language, Bjarne Strostrup, and also by Herb Sutter at Microsoft, who is their lead in developing C++ for Windows. And also half of C++'s greatest strength is in its core language, but the other half really is in its third-party libraries. And they're what make the language do very cool things. And I would really rather not have you reinvent the wheel. So I just have some links to the Boost libraries, which we have used in the past, and they cover a whole bevy of different topics relating to how we manage memory, to how we parse command line arguments, and so on. And also to the Eigen library, which I'll talk about more tomorrow, which deals with linear algebra done efficiently. So I'm going to start with the simplest programming exercise imaginable, which is just a variation of the Hello World program. And surprisingly, this program uses many of the core features of C++, but people new to the language don't realize what they're using and how it all works together. So I'm going to introduce a few new concepts one by one and show where they are relevant either to here or to some contrived examples or to different parts of JEDI. And I completely admit that there are many different features to go through, so I'm planning on following a vaguely historical progression of the language. So I'll talk about C, because C++ was based on C and its benefits and drawbacks a lot. And this is in many ways very similar to the situation with Fortran, so hopefully it's not too much of a leap for everyone. And I'll discuss what C++ then brought to C. So back in the 1900s, people started making calculators, and these calculators first were using vacuum tubes and then very simple transistors. Like even up through the 1950s, you had, say, an 8-transistor radio. And these calculators were very simple devices, and they frequently lacked a disk or really any memory and had really the most basic I/O. But still, these calculators powered some of the first attempts at weather modeling and NASA missions and the like. Like even the original Kalman filter was written for Apollo 11, and it was executed in about 60 statements of code. And slowly, additional features like registers and persistent memory got added in. And originally, you would write a set of machine instructions manually that the machine worked on one by one, and this got really tedious very quickly. So the first basic assemblers were invented that basically replayed macros or just repetitive statements to do the same thing a whole lot faster. But then people got tired of writing these macros and having to know the intrinsic differences of every computing device, like its instruction set or the endianness of numbers or the arrangement of the CPU's registers, and they started making the first programming languages. And Fortran really was one of these early ones and had very rapid development up through the 1970s and even into the 1990s. But on a parallel track, C was created to act as a systems language, and that is one that retained the ability to manipulate the lower levels of a system while still providing enough high-level features to be usable. So it's been a language of choice for operating systems. So it still powers the Linux kernels and it still powers the core of Windows itself. And it's different from Fortran in that it needs to use these lower level concepts and expose them, such as using direct memory pointers and supporting several different semantics for transferring data between functions. By that I mean things like pass by value versus pass by reference. But since so much was invested in developing these features for the language and you wanted to focus on performance, they really are used extensively, and I am going to mention them in some of the later slides. You'll note on this slide, there are a couple of differences between C and Fortran. So for example, Fortran has a much stronger support for multidimensional arrays, whereas for C's arrays, they're very simplistic in comparison, but C is a lot more expanded in memory manipulation again. So let's start off with C and sort of jump into C++. And it helps to give you all an idea of what functions look like. So any C or C++ program is built up from a series of functions like the one illustrated here. And I'm just going to go through and show you how you can read this. But first, let me ask Kat, can everyone see my mouse pointer this time? Or is it not showing?
Yes, I can see it.
Yeah, it is showing for
Excellent.
me.
Okay. So the first thing then is that this is what a C function looks like. And every function in C or in C++ starts with a declaration. Okay, and that's these two lines right here. So you have the name of the function, then you've got a set of parentheses, and inside of these parentheses, you have parameters that you can pass into the function when you're calling this function. So very similar to Fortran. Each of these parameters has a type because C is a very strongly typed language, and optionally you can give each parameter a name. Unlike in Fortran, C and C++ by default use what's called pass-by-value semantics, which means that any inputs to your function get copied. You don't just reference them in memory. But if you do see an asterisk or an ampersand, that means that you're using a different type of passing semantics, in which case you're not making a copy. Also, slightly unlike Fortran, this function has a return type. Actually, Fortran has return types for functions, but C doesn't have Fortran-like procedures. So everything is viewed as a function. And if a function returns nothing, like with a Fortran procedure, then its return type is going to be indicated by type void. Now that we've declared a function, we have braces that denote the function body, and braces are also used to denote different levels of scope. So, for example, this variable that we're declaring, return value, is only accessible inside of this function body or at this level of braces. If I declared another value here, it will be accessible only at this level of scope and not to the overall function. You can't access something inside of a scope outside of that scope. And also, speaking of the function body again, variables have a strongly defined type, and C provides many different types, but C's types are different from Fortran's types. Unlike with Fortran, especially, unsigned integers and unsigned values are also available. Also, for types, if you declare a variable const, then you can initialize the variable to some value, but then you can't subsequently change that value. So this is really useful if you're calling a function and passing in data to it by, say, reference or by pointer, and you want to make sure that it's immutable and that the function doesn't change it. Anyways, on the whole, C really can be viewed as a series of functions calling functions, starting with a function that we just named main, and just extending until a program finishes its own execution. Now, C was designed again for systems programming, and it does suffer from a couple of annoying drawbacks that led to the development of C with classes, which later got renamed C++ from 1979 up until like the late 90s when it got standardized, and then to continuous development even today. There are a few languages like Objective-C that also grapple with the same issues, and they try and solve these issues in sort of parallel manners. So the first one that I like to point out is the lack of scope and overloading. And Fortran recently did address this in, say, 2003 and 2008, and these are both very closely related. So first is the lack of scope, and that basically is every function in C has the same level of scope, and no two functions can have the same name because then you'd have a symbol clash off in the compiler and the linker. So this would cause some headaches. So for example, many of the very simple names are already taken, like open and close and read or write. And sure, these are operating system level functions, but also some very simple names get used inside of LayPack or inside of HDF4. So you have trouble linking certain libraries together. And this caused developers to start adding prefixes to every different function that they use, or having weird creative spellings depending on what you wanted to do. And the names have been getting longer and longer. So one of the concepts that C++ introduces is the concept of what's called a namespace, which lets you have a logical group of functions. So you can think of a namespace as a set of identifiers that are under the same logical scope. So in this case, I have a little code example off to the left. So we have two namespaces here, JEDI base and Yoda, okay? And then we declare functions like do something in both JEDI base and in Yoda, and they don't conflict with each other. So basically, you can have the same function name and just a different level of scope. And if you want to decide which one you want to use, or if you want to state which one you want to use, you can either state it very explicitly, or you can also use what's called a using namespace statement, where you sort of are just aliasing all those functions into your current level of scope and how you're in your current block of code. So say that we use something called using namespace JEDI base. Then you no longer have to prefix the do something else function with the namespace name. And now inside of JEDI base, you can call get current month, just like this. Wherever you see two colons together, that usually means that you're dealing with a namespace in some way or form. Now, the other initial problem is really closely related. So in C, you can't have two functions that have the same name, even if they take different arguments. So if you want to do the same task on different data types, then you have to come up with different function names. And this is where this feature becomes very useful because you want to do math. And when you want to do math, sometimes you're dealing with floating point numbers in single precision versus a floating point number in double precision or extended precision, or you're dealing with integers. And you really don't want to have to constantly redefine your functions and have creative names. And if you can't overload these names, you have to produce a lot of different possible names. So if you're trying to do math in C, what you generally have to do is you have to read a table like this. You have to say, okay, I want to do a sine. Then is my function input a floating point number, a double, a long double? And then you have to go through and you have to manually define a separate function for every type that you can expect. And then each one has its own separate name. So again, this gets really verbose really fast. With C++, you can overload, so all of these functions can have the same name, but they can take different types of arguments. So instead of having 6 different types of sine, you just have one, and it's called sine. The other main limitation of why we got C++ is that there weren't any true objects. And what's an object, you might ask? And I'll get to the full definition of that in a bit, but basically, the language could only handle basic structures of data types, which were themselves built out of the very primitive types available to the language. But as objects got more and more complicated, you had to add in auxiliary functions to manipulate them. But these structures had no concept of life cycle, so that you had to manually allocate memory, you had to manually initialize an object, you had to manually free or deallocate an object when done, and this was really mistake prone. You also had to manually check the result of every function call for errors, which became very verbose and time consuming. So here's an example from the Windows API. And this consists of a lot of low-level C functions. So don't read it too carefully, but I'll just give some examples. So in this case, if you wanted to write something out to just the regular output that you had to call get standard handle to get the standard output handle. And that initialized a special type of C structure. Then you had to manually check for an error. And then you would manipulate it or call a function which talked to that structure and read some data inside of it. And then you would have to close it manually again. And if you forgot to close it, then you had a resource leak. If you didn't check that it had constructed itself properly or that you had initialized it properly, then you would have random other errors that were very hard to debug inside of your system. So one other thing that C was lacking is that there wasn't much of a standard library that everyone knew how to use. So it provides a standard library, but these are more geared towards system level functions like opening a file and getting a file pointer. If you wanted to do anything very sophisticated, say defining your own file format or doing linear algebra, then you either had to do it yourself, which basically meant reinvent the wheel, or look at what somebody else did. But because there wasn't a standard, you had a bunch of different libraries that all tried to implement these features, and then other people built off of those libraries, but those core base libraries were not consistent with each other. So what that meant is that there were, say, 3 different ways of doing linear algebra that people came up with. And then somebody built a bit of code off of one of those libraries. But then say that you just wanted to extract the low-level algebra inside. You might have been using a different library or different semantics, and then you had to spend a lot of time writing boilerplate code, translating their conception of the same concept to somebody else's conception. Effectively, it was a gigantic waste of time. There wasn't a support for things like standard data containers. Like in programming world, you have concepts of a linked list, and the C standard library had no support for a linked list. So then you had 5 different implementations of that. So C++ tried to solve these issues. Or from the reverse side, you might say that C++ adds on its own level of complexity and frustration to how it does things. But again, I find that it helps to understand where the language came from to see why it is the way that it is and to see where it's going. So let's talk about objects. So inside Fortran 2003 and 2008, and in parts of Fortran 90, you start to get this feature too. So originally, C introduced structures as a way to encapsulate groups of related data together. So think of having a data record, and storing objects by record or storing data by record, as opposed to having a separate array for each and every variable that you have inside of your models. And when you do this encapsulation, you generally find that you want to add in convenience functions for manipulating each record. And that's the first step down the road towards object-oriented programming. So say, for example, that you're dealing with some metadata and you have a structure that looks like this, where you're storing your location IDs, your times, your locations, the pressure levels, and then you're dealing with some pointers. You might want to have a convenience function to initialize the structure to set everything to a default value. You might also have a freeing structure to deallocate it in memory. And then you might also have some other convenience functions to manipulate this. So C++ brings these convenience functions into your data structure itself. So what is an object? It's basically an instance of a class or the working entity of a class. And a class is a template or a blueprint about what an object can do. So here's just a very tiny example. We're defining a class called a rectangle, and we use this to manipulate rectangles. So I'll go through what a class looks like, or the details of how a class is laid out in a little bit also. But the point is that you have a class called rectangle, and then we have a specific instance of the class called rect. The class has its own members, so you can have both data as members and you can have functions that work on the data inside the class. So this is similar to like defining like an integer. Instead, you define a rectangle and then you can manipulate the rectangle. So again, it's this encapsulation that gives us an object. So you might wonder, like, why do we use objects? And there are 4 general concepts that a class actually ties together, and I'm going to go through each one of these for you. So first, we've got encapsulation. We basically stick the functions that we work with in the class inside the class to avoid having to read too much when programming. And then we have inheritance. So think of rectangles and think of a specific type of rectangle, like a square. Okay, a square is a type of rectangle, and in coding, you would want to be able to treat similar objects in a similar manner. Or basically, you can have a base object and you can have something that derives it or specializes it. Okay, then we have abstraction. In this case, we want to be able to give consistent interfaces to end users, and we want to hide unnecessarily implementation details from the end users, and we don't want them to muck around with object internals and mess things up. And then there's also a related concept called polymorphism, and that's to use the same interface to operate on different types of objects. So for example, we have rectangles and squares, and we can have a polymorphic function that just takes in a rectangle, and you can pass a square into that too, and you don't have to write any specialized handling code. So just to go through these one by one, here's an example of encapsulation again. So we've got a class of rectangles, and here's how you can read a class definition. So again, we define a class with the keyword called class, and then we have the name of the class, and then we've got some braces. And for any class definition, we're going to end that with a semicolon here. That in C++ or C means that it's the end of a logical statement. Inside the class, we have members that may or may not be accessible to an end user. These can be private or public or protected. So this is how you denote things like that. And private members mean that an external user of the class can't access that data directly. Any of the functions in the class can access the data, but anything else coming from outside of the class can't access it directly. They might have to call a certain function to read that or to write it. Again, we want to encapsulate the interface and have people access code from clearly defined boundaries or using clearly documented procedures. So say that we want to update these, we would call, say, the set values function, and that's how an outside user could modify these. We also have the bound functions inside the class that are encapsulated with it, things like area and perimeter. We could call like rectangle.area, and it would get the area of a specific rectangle, and it would just return a value to us. Now, also with classes, we have objects that have functions, and we have all the data members inside of a class like a struct. So we have to establish a type of object life cycle. So basically, when an object is first made in C++, we first allocate all the space to store its data, and then we call some functions or initialize the data to sensible default values. And this is accomplished in what is called a constructor. So a constructor, one second. A constructor is a function that runs right when an object is first instantiated, or right when you first allocate memory to the object. How do you fill it in with sensible defaults? The constructor has the same name as the class. So if you're creating a class called rectangle, the constructor's name is also rectangle. So generally, we want to produce objects that are entirely initialized or basically ready to use as soon as the object itself is created. You don't want weird situations where your object is only halfway ready or halfway available. Now, conversely, when an object is done being used, when it goes out of scope in a function, then it gets destroyed, and a destructor frees up any of the resources that the object has acquired. So you have safe cleanup. And any destructor has the same name as the class, but it starts with a tilde. So again, this is just so that you can figure out how to read things like this. So here's an example of both in class rectangle. This would be a constructor, and this would be a destructor. In this case, the destructor isn't doing anything, but it does get called when the object leaves scope or when you're destroying the object. Another major concept of classes is inheritance. And I mentioned before, a square is a certain type of rectangle, and it can inherit the same functions that a rectangle has for calculating area and perimeter. It could also introduce new functions. I'm not going to show those in this example, but this is how you can express inheritance. A square is a child class of a rectangle, and then you use a colon and you say public rectangle. Okay, the third concept is back to one of those C++ limitations, and that's polymorphism and overloading. So I talked about this before. So the first example is function overloading. So multiple functions can have the same name, but can take different arguments and can get different function signatures. So here's how C would handle taking the power of a double versus the power of a floating point number. You have to have two different function names. Here's how we do it in C++. We're both calling standard POW. This denotes that we're using a function in the C++ standard library, which is included by one of these guys up here. And in this case, it's included from CMath. And I'll talk about the standard library in tomorrow's lecture and just hint at it today. But the takeaway, though, is that with polymorphism, the function can take different types. And then instead of just overloading a function, we can combine this with inheritance, and we can overload the functions inside of a class. So in this case, we have a class defining a point in two-dimensional space. And then we can inherit from this, and we can define a Cartesian point, or we can define a polar point. In this case, a Cartesian point has x and y coordinates inside, and we can get x and y. And then we also have a polar point, which instead of having x and y has a distance from the center and an angle. And you'll see with inheritance, we can define functions like x and y. For a Cartesian point, these are trivial. For a polar point, they have a different definition, but they provide the same interface to an end user. And that's the key point of overloading. So the right function gets called no matter the type of object that gets passed. So whether you pass in directly a Cartesian point or a polar point to a function, then you can still do the same operation. And then the third really cool thing about this is that you can combine all of these features together, and you can also overload operators inside of a class. So these are what are called operators in programming. So addition, subtraction, multiplication, division, equalities, and so on. So this lets us do things like symbolic math on different types of objects, even on things like arrays and other containers. Or in this example here, we can do symbolic math on complex numbers. So we can define a complex number class, and then we can overload the operator plus. So instead of then going piecewise and saying, okay, let's add up the real components and the imaginary components together. The user doesn't have to care about that. They can just say complex number C3 equals C1 plus C2. So this is exceedingly useful, again, for manipulating large matrices or doing linear algebra or doing other things like stream manipulations. It all combines together. Now that we've gotten classes discussed a little bit, I'm also going to very briefly outline templates for you guys. So there have been entire books written on the subject and how to use templates, and I'm not going to go into the details for the interest of time, but I will show you how they're used in day-to-day tasks, however. So a template is this final concept of C++, and it's another simple and really powerful tool. And this is basically that you do not want to have to rewrite all of your functions constantly and write a lot of boilerplate if you're just changing the function parameters. So in this case, we can, instead of defining a function called, say, mymax, which takes an integer and returns an integer, and manually defining another one that would take a character and then return that character, you can instead combine these into a template. So they're all denoted with the name template, and then type name, and then the type. And then this acts as sort of an alias. So here's the generic definition of this maximum value function. If you stick substitute in integer for t, then you get this definition. If you substitute in a character here, here, and here, then you would get this other definition. So that's the concept of templates. So really, by just defining a template, you can call this template with different types of data, and you can get the same result without having to write a lot of extra stuff. And we use templates throughout OOPS and in several places inside of Yoda and UFO. Just some very quick template details for you guys. You can make templates out of individual variables. So this way you don't have to constantly redefine a fundamental constant like pi, and you don't have to define a pi as a float, a pi as an integer, a pi as a double. You can also have templates of classes, and it would look something like this. So my class specialized as an integer. And you can also define templates of functions. And you can also have more than one template parameter. So you can have a function which has parameters of an integer and a double. And here's how you would actually define it. Okay, one other point before you go into the exercise, and that is that C has a standard library and C++ has a standard template library. And I'll explain tomorrow with a bunch of examples. And let's just say that the standard template library is built into every single C++ compiler. It's always available, and this is always very convenient because it is a big library and everything in there is based off of templates in some way or another. So it provides you with standardized containers for data or sets of data together, and these can be expressed as sets or as vectors or as one-to-many mappings. You also have some algorithms for doing data searches or for math or for memory management. It also has a complete library of being able to manipulate I/O for files and on the console. Again, the takeaway here is that there is a lot that C++ offers and you really should explore it. But in summary, however, I want to go back to that initial Hello World program that I showed you at the very beginning and just say, with all these concepts, they all apply in a bunch of different ways, even at a very low level or at a very simple level. So first, include IO stream. If you read something like this and you see a little bracelet that looks like this, you're probably dealing with a header file found in the standard template library, which means that it is very well documented and the documentation is on a whole bunch of websites so you can know how to use it. In Hello World, we use namespace standard, and this provides this symbol called cout. It also encapsulates all of the functions that IO stream introduces that you can call. Okay, back with C, I showed you how a function definition works and what it looks like. So here's a function. We define some variables, And then we hit a C++ feature, cout. This is a stream for the standard template library that allows you to access the console. Now we have these two less than symbols. This is actually a type of operator, and we've overloaded this operator. This overload is actually accomplished using a template, so we don't need to do anything special, whether or we pass in a character string, or whether we pass in an integer, or whether we pass in a floating point value. It all looks the same. And then at the very end, we have a statement called return, indicating that the program executed without error. Anyways, I hope that this talk helps you understand C++ a little bit better, if not in practice, then at least in theory, so that you can glance at a program and get a rough idea of what's going on. So you should be prepared enough for this morning's practical. And if you want to know more, then there are a lot of resources out there. And this, again, is one of the big benefits of using a popular language. So let me just stop now and say thank you for your attention and ask if you have any questions.